Electrostatics 11, electric dipole continues from yesterday. We have defined the dipole moment by suspending the dipole in a uniform electric field. We saw that it experienced the torque. In finding out this torque, we came across a quantity called P, that is electric dipole moment, direction of which is from minus to plus charge, and the magnitude of which is charge into distance between the charges, plus Q minus Q. So just Q you will take, not 2Q there. Q into L between the two charges. That's what we call electric dipole moment. So that becomes the property of the dipole now. So whenever we mention a dipole, we'll mention P bar, vector P. Right. Now, we'll go back again to that figure. There was a uniform electric field in which the dipole is suspended the uniform field is shown by the parallel field lines. Okay. Now, the dipole is turned here. Supposing the initial position was here, the dipole was turning because of the torque applied by the electric field. This is Q. This is Q. The length we took as L. People might take even 2L. Here, of course, is not necessary. We can take L somewhere else later when you find out the electric field strength. We'll take the distance between the charges to be 2L because we'll get half the length in the formula. So instead of writing L by 2 there, we'll write L. But there's nothing like 2L to be the distance. People always get confused with this. When half of the length comes there, if I take L here, L by 2 comes. If I take 2L there, L comes. So to make the formulas look clean, people take 2L there. But otherwise, it's basically the length between the charges, which is L, is enough. Now, why did I draw this figure again? Remember, it is half done. Whatever we did yesterday is not over yet. When a dipole turns like this, work will be done. The electric field being electrostatic field, potential energy will be stored. So here, the potential energy stored in the dipole. As a result of the torque acting on it. So you remember potential energy definition was like this for a force. U2 minus U1 equals minus 122 F conservative dot dr. This is the definition of potential energy when conservative force does work. But here conservative force develops a torque and torque does work in rotating it. So you can write U2 minus U1 equals minus 122 torque dot d theta. Okay, there we had this. Here we have this. Easy to remember. If you remember the main thing, Others will follow automatically. Okay. Now u2 u1. Let us keep it like that only, but I'll write it like this because 2 1 here refer to the positions in terms of theta. This is in general theta we told previously. The angle between this p vector and e vector is theta. I'll show it separately for clarity. This will be p vector, this is e vector. So this is our angle, theta. Look, p cross e will be which way? Into the plane, isn't it? Right hand thumb rule.
Yes.
So tau is into the plane. You can say tau equals, if you want to put it in IJK format, minus PE sine theta k cap, isn't it?
Yes, sir.
D theta is also a vector. Infinitesimally small angles are made vectors. So this is d theta k cap. Why do you know d theta? If this is the positive x-axis, in the anti-clockwise direction, we take d theta to be positive like this in the right hand thumb again, right hand thumb direction. If we turn like this, we put it in the same plane of the paper. This is positive x-axis. We're turning the angle like this. The angle measured like this will make the vector d theta like this. Hope you followed again. Right hand thumb rule. Turn in the anti-clockwise direction. This is the anti-clockwise direction. And if the angle is measured in the anti-clockwise direction, it will be measured like that by convention. So d theta is a vector like this. So here,
Yes, sir.
u at theta 2 minus u at theta 1 is equal to minus theta 1 to theta 2, this one. Do you understand?
Yes, sir.
So will the torque be 0? This is dot product, not cross product, isn't it? So minus PE sine theta, torque is, sorry, work done, dot d theta k. So what do I get? This minus minus makes it plus theta 1 to theta 2 minus PE sine theta d theta. Sorry, minus already gone, right?
Yes, sir. Plus.
K dot k is 1. What do you say? So PE, what is integral sine theta?
Minus cos theta.
Between
Theta 1 to theta 2.
theta 2. So what do I get here? Cos theta 1 minus cos theta 2, isn't it? Minus cos theta 2 minus minus of cos theta 1. Do you understand that? I
Yes.
don't want to write one more step. So this is u at theta 2 minus u at theta 1, a generalized formula. Okay. But if I take the 90-degree position as the reference position where the potential energy is 0, I can write, but if we take at theta 2 equals 90 degrees, u theta 2 is 0, then I can write 0 minus u at theta is equal to P into cos 90 0, cos theta. So u at theta equals now minus PE cos theta, which is minus P dot E. Very simplified formula again. Do that carefully, but ask doubts. If you say it's over, you followed everything, I won't be impressed. Actually, if people come prepared, they'll get doubts. Actually, there's one more problem we have. People don't read in the middle, in the beginning. Complete the calculation. After that, we'll go for the next. You can always use this formula when some theta 1, theta 2 general are given, but otherwise, if I take potential energy to be 0 here, that's what we learned about potential energy, right? We had basically defined potential energy difference. But if you make potential energy at 1.0, you get the potential energy at the other point. That's what we know already, right?
Yes, sir.
So there was a P cross E, which was torque, right? Now there is U minus P dot E. But remember, when you say U, you need to know this PE cos theta will be the theta which the dipole is making with E. And at 9 degrees, we thought it is 0. So that has to be kept in mind. Any question, children? Look, this torque is trying to decrease the angle with E, or this torque is trying to make the dipole align with E. Initially, it was 90 degrees, but now it became less. And when the dipole, the plus and minus, this line coincides with the E, it is along with the E. So the dipole is that way. The electric field is that way doing a negative work. That's what we got as minus P sine theta there.
Sir, if it becomes like parallel to E, then the positive and negative sides, won't they be on the same line of action?
They will be. At that moment, torque would be 0.
Torque will be 0.
At that moment only. It might turn even more, right?
Yes, sir, because it will be there.
At this 90-degree position, torque is maximum. In that position, torque is 0.
Yes.
Torque is a function of theta, P sine theta, right?
Yes, sir. So here, basically, it is trying to reduce the torque till it becomes parallel.
Who is trying to reduce the torque? Who is trying to reduce the torque? That's not a good statement. We are trying to reduce the angle, I told.
Yes, sir. But then from maximum, it is becoming 0, the torque.
But no, what are you saying? You are saying it is trying to reduce the torque means who? Torque is reducing. As the torque is the one which is trying to turn the dipole, and as the torque reduces, as the dipole is turning, torque is reduced. No one is reducing torque.
Yes, sir. Now
E is producing torque, Sriya.
Yes.
Because of torque, the dipole turned, but the dipole turned, therefore torque became less because the angle is decreasing.
Yes, sir. So as it is turning, the torque is being reduced.
Okay, children, can I go to the next page?
Yes.
Now, this is potential energy stored in the dipole. And then we'll go for that E due to the electric dipole. That's how we started our lesson, if you remember. We said we are having the electric field of a point charge. But practically, we have seen that there's a single unit called dipole, which exists in the nature, minus q plus q held together. This minus q plus q are separated by some distance. Therefore, there will be electric field around it. One point of interest is what kind of a field it forms around it, right? So that was our main idea. But in the beginning, in the middle, we defined a quantity called electric dipole moment, which is the defining physical quantity for the dipole. So once we know that, we can go for finding out the E of the electric dipole. So next thing is that is electric field strength, electric field strength due to an electric dipole. Once you have a dipole like this, a minus charge and a plus charge like this, this is q minus q, this is plus q. There are various points around it. So first we'll try to find out the electric field strength on the axis. You can find out at a general point, that's okay. But in the beginning, it will be easier to look at these 2 points. One is the axis, the other is the equatorial line. Since we are going to get half the length in the final formula, we'll take the length of the dipole to be 2L. This is only for our convenience. At a distance R along the axis, this is called the axis or axial line. At a point here, we would like to find out E. So the heading will be on the axial line or on the axis. The axis, we would like to find out electric field strength. Okay.
Yes.
Superposition. Plus q causes a field, minus q causes a field, right? So E will be the vector sum of E due to plus q plus E due to
Minus q.
minus q. Isn't it so?
Yes, sir.
Now,
Yes.
E due to plus q, if you check, it will be like this, a repulsive field. right? E due to minus Q towards it. Isn't it so?
Yes.
Huh?
Yes.
E due to plus Q will be more. Why? The distance is less. E due to minus Q will be less. The distance is more by R square all the time, isn't it? So the angle
Yes.
between the two is how much?
180.
They're opposite. So mod E will be simply U due to mod of this one minus this one, right? This is a vector sum we said. Write in IJK, you can straight away write in IJK form, otherwise only magnitudes you can take. Huh?
Yes.
If you remove this E bar, write I here also, it will be okay. Huh? Now this will E due to plus Q will be how much? K Q by this distance is R from the center. So from here to here, the distance is R minus L, right? Huh?
Yes, sir.
E due to minus Q, R plus L. Hope people followed.
Yes, sir.
So this will be KQ into isn't it? It implies E equals, tell me, KQ into
4R.
R plus L whole square minus by, is it okay? In one step I wrote. Huh? Hello.
Yes, sir.
This is it okay, everybody? The maths part of it. This also I'll write as K into Q into 2L into 2 into R by, this is 2 into K into Q into 2L is P. And the direction will be this, because this is great and plus Q is nearer, it will be along the axis only, but E will be this way, net E. Had there been minus this side, like if I reverse it, minus was here, plus was there, still the magnitude would be same, but E would be towards the dipole along the axis. So this is the magnitude and the direction I mentioned. Tell me. And a special case of interest would be if L is less than R. Very naturally, for molecular dipoles, the distance between the dipoles is of the order of few angstrom units, right? So where you find out the field to the dipole, that will be large. Water molecule here, 1 centimeter, 2 centimeters also is very large compared to the dipole length. So very reasonable that is. Huh? So E will be 2 kpr by ignoring L square r to the power 4, finally 2 kp by
RQ.
Look, for a single charge, kq by r square. For a double charge, which is called a dipole, plus q minus q, separated by some distance, E is inversely proportional to RQ. Look at this. And one quantity defining that is P. Q and L between the length between the charges will be coming into picture. So leaving it in terms of QL, all that we write P here. That's where we defined our P first. This is the electric field strength on the axis of a dipole. If it is over, we'll go for the next one.
Sir, if we need to find it on the other side, left side of minus q.
Here, also similar formula, right?
Yes,
But
sir,
it will be
but
towards.
so it will be negative.
It will be negative means towards it.
Yes.
See, actually, don't get into this negative business for a vector quantity. Once you say direction is towards left, it is taken care.
Sir,
Uh,
there the magnitude of E due to minus Q will be more.
More. That's why it is towards minus.
Minus.
Yes.
The plus sign, minus sign are important for scalars. Do you know?
Yes.
And in vector form also, you'll write plus or minus if you are putting it in vector form, IJK form. Otherwise, you give the direction separately and magnitude separately. Direction with the arrow, magnitude with the number. So by putting the direction there, once again, don't put a minus sign.
Yes.
If you put a minus sign along with this, write I cap, minus something into I cap. So it takes care of it. But
Yes,
since scalars do not have that kind of a facility, and if you have to differentiate between two opposing things like negative potential, positive potential, we need to mention it. There's no other way. There's nothing like negative electric field strength and positive electric field strength. Electric field strength is a vector automatically. So if you show it in vector form, the direction is already taken care. Okay. Can I continue for the next one?
Yes.
Yes, sir.
I'm going ahead. So electric field strength on the at a point on the or on the equatorial line. It's basically the perpendicular bisector. Nothing else of a dipole. Okay. Come back here for the figure, minus q here, plus q there. Once again, let us consider distance to be 2L only. See, while defining P there, I simply took L only, try to understand. But now I'm taking 2L, so have that difference in your mind. Whether you take L or 2L, it is finally the distance between the charges. Right. Now, what is this equatorial line? A perpendicular bisector, I told you. Okay. At this point, what is E? Once again, as usual, E is because of both plus Q1
minus Q1.
Vector sum of plus Q1 minus Q. So let us show it practically. Let me draw this here. So plus Q's E will be which way? Away from it or not?
Yes, sir.
Like this. Just a minute. It's like this. E because of plus Q charge. Right? Hello. And due to minus, yes. How is it?
Towards the minus.
Towards the minus. All right. So it's like this. So both are vectors. And luckily, both the magnitudes would be same, children, isn't it? So this is L, this is R, distance from the center. So this distance is going to be what?
R square plus L square.
So Q is same, distance is same for both of them, isn't it?
Yes.
So the magnitudes of this and this are going to be same. Hello?
Yes.
So if you say this angle is theta, for example, this angle is also theta. You can resolve this into components to find out the vector sum, or you can apply the cosine rule also, but applying components will be much easier. If this is theta, this is going to be theta, right? Huh?
Yes.
So component of this will be what? E due to minus q cos theta.
Cos theta.
This is E due to minus q sine theta. Similarly, if this is theta, that is theta. So this is E due to plus q cos theta. And in this direction, E due to minus q sine theta. This is also E due to minus q sine theta. So these vertical components cancel out, isn't it so? Huh?
Yes, sir.
So E will be now in magnitude form. I'm writing, you see, E due to plus q cos theta plus E due to minus q cos theta. No integration, only two charges are there. Try to understand. Huh? So E due to plus q is equal to E due to minus q is equal to, in magnitude terms, kq by r square plus L square under root whole square, right? So kq by r square plus L square. Do you follow this? So E will be, both magnitudes are same, right? So it will be 2 into this into cos theta, right? 2e cos theta. Am I right? So
Yes, sir.
so 2 into kq by r square plus L square cos theta. Let us write cos theta also, so that everything comes in distance form. Cos theta will be L by root of r square plus L square, isn't it?
Yes, sir.
So 2kql. K into q into 12 is what? P by the power
3z.
and the direction of E will be what? The very important thing. Many places you need to straight away do it. Direction E is
Between both of them.
between both of them is right. That's correct. Bisect the angle between them, but it is towards, parallel to the axis and towards minus. Towards minus means on the side of the minus, right?
Yes, sir. Towards the left.
On the side of the minus sign. Minus q. Hope you followed. Parallel to the axis and on the side of the minus, this way. Huh? Towards this minus, actually. Do you follow this one? It won't be this way. It will be always like this, and the arrow will be going towards minus. Parallel, of course, not here, there. Okay.
Yes.
Yes.
Whereas on the axis you have seen it is along the axis only, either towards the dipole or away from the dipole. But on the equatorial line, it is parallel to the axis and the direction is towards minus. Okay. Even
Yes.
towards can be written. That's not a. So this is to be noted. All right. In a similar way, like we did previously, if or when our L is less than R, E will be how much? K P by, ignoring this,
R cube.
and you can notice it was 2 kp by r cube on the axis. So E on the axis divided by E on the equatorial line for the same distance would be 2. This was 2 kp by r cube. Refer back. 2 kp by r cube. Here it is kp by r cube. Okay.
Sir, but only for L less than.
Yeah. And I told you already, L less than R is very practical. I told you already, no? Dipoles are basically, practically they occur where? At a molecular level, right? Huh?
Yes.
So for a molecule, the dipole length is very, very small as compared to the distance around the dipole where you would like to find the electric field. Huh? So it's very reasonable. Not very reasonable. It's more practical than the first formula. So is this over, children?
Yes, sir.
So can I go to the next one?
Yes, sir.
Let us find out at a general point. We found out on the axis, we found out on the equatorial line, but why not find out at some other point? So E due to a dipole at r comma theta, and we'll do it in a specific case of L less than R. At r comma theta is a general point. I'll show you what it means. This is minus q and then plus q I have. So once again, as usual, I'll take the distance to be 2L. At some point there, I wanted to know the field. This is theta, that is R. Hope you understood now. This distance is R to the point. So at that point, we would like to find out E. And in a specific case of L less than R, because that's more important for us for problem solving. We can also do in general terms, children. But the mass becomes slightly lengthier, so we would like to avoid that crowding of the characters in the formulas. How do we do that? We follow a specific procedure for this. We already know E on the axis for a small dipole was what? 2kp by r cubed. E on the equatorial line was how much? Kp by r cubed. I would like to use these two formulas anyway, because we said L less than R. I want to use that, for which I will take my P. P is like this for this, isn't it? Dipole moment vector is like this. This vector P, I would like to consider that to be two dipoles. One, this one, parallel to this line. This is P cos theta, because this is theta, and then perpendicular to it. This is P sin theta. So it's equal to two dipoles now. And this point is on the axis of this P cos theta dipole and on the equatorial line of the P sin theta dipole. Do you follow? So I can say, see, if this is this way, this is minus, this is plus like thing. So this will be E parallel there. We can call it E parallel. This E parallel is due to whom? Due to P cos theta dipole. This is E parallel. Right? And because of this dipole, it is towards minus. If the arrow is like this, it means this is plus, this is minus, this is plus. So E perpendicular will be like this. Just now I told it will be towards minus. This is E perpendicular. Why am I calling it E perpendicular? Perpendicular to this R line. So the E, the total E would be somewhat like this. The resultant of these two. Hope people followed it. Now I can write E parallel equals. If people are taking everything silently, I'll be always worried. E parallel equals, from here I can write 2k p cos theta by r cubed. Because the dipole is here p cos theta, not p. E perpendicular will be kp sin theta by r cubed. So the total E would be vector sum of these two things, E parallel square plus E perpendicular square. If you simplify, tell me what you get. I won't do it for you. And also this angle alpha could be found. Tan alpha equal, this is the magnitude part, and tan alpha will be simply E perpendicular by E parallel. This will be E perpendicular is 2p cos theta by r cubed, right? Sorry, kp sin theta by r cubed. That is 2kp cos theta by r cubed. What will I get now? Hello?
Tan theta by 2.
Tan theta by 2. So this is the direction of E there. But this magnitude thing I want. So see if you understood the idea.
So E axis and E equatorial, we took it with minus q and plus q as axis.
Can you be more clear in your wording?
So like when we said E axis, we took the line between minus q and plus q.
That's the axis for the original dipole, right? So
yes.
now
Then
this
again,
P is taken as two dipoles with the dipole moment P cos theta and dipole moment P sin theta. So it's now two dipoles, one dipole here, one dipole here. And for this dipole, it is on the axis. For this dipole, it is on the equatorial line. We applied the old idea.
yes, sir. So we're splitting this, meaning taking it like two dipoles.
Two dipoles.
Yes, sir. Okay.
So this final thing I want, because if I write it, I know it. If I write it, you write it directly. I want you to calculate. I want you to calculate that and write it finally. This whole geometry should be in the mind. If I have a general point like that, E will be like that. It can be taken as two parts, E parallel, E perpendicular. So if that is there, when you look at a problem, automatically the brain connects. So are you ready with the final answer?
Sir,
Yes.
Kp by r cube into
Kp by r cube into
1 plus 3 cos square theta.
1 plus 3 cos square theta. That's correct. Now this equation you can check back. If theta is 0, the point is here on the axis, right? Hello, this theta is 0 means this point is here. My cursor, can you see? Is it visible?
Yes, sir.
So you just put theta equals 0 here. 3 plus 1, 4, 2 kp by r cube, isn't it? If theta is 0, it is axis. And the formula reduces to that only, 2 kp by r cubed. And theta is 90. it is here, this one. So it is the perpendicular bisector or the equatorial line. The formula reduces to this is 0. So Kp by r cubed. Can you see the limiting case of this? So this becomes a general case now. At r comma theta. That's what I mean by at r comma theta. Neither on the x-axis here nor on the y-axis there, but r and theta. So if this is over, I'll summarize. We have finished one very big unit. Of course, one or two things are still there, but yeah, finish it fast, everybody. One more thing is there actually. Of course, rest applications we could do later in problem solving. The lesson is, I can say, is over.
Sir,
Just 1 second. Yes, Shreya.
sir, so here we are making the dipole into two dipoles and defining electric field strength with respect to both of those dipoles and taking their vector sum.
True. Why like that, you think, or what? Is it okay for you?
Yes,
Is it
sir,
all
like
right? Is it all right or not?
yes.
Now, one more thing actually. Let me finish off that because it's now less time. 4 to 5 minutes we have. Let me finish off the next thing. Can I continue for the next page?
Yes.
Now, force on a dipole in a non-uniform field. Force on a dipole in a non-uniform electric field. A very practically important thing. Look, you all know, you take a comb and move it over a dry hair and then put it near the near small piece of paper. What do you see?
The paper is attracted to the
Attracted, huh? Like I can try the picture also if possible. Just a minute. These are the teeth of the comb if you want. Okay. Like this, have a comb, for example. Now, something happens when you burrow it into your hair, and then some small piece of paper, we bring this comb to the small piece of paper, and they get attracted. Probably when you rub it against your hair, some charges are formed, maybe, so something happens, they are moved, attracted. How do you explain that? Before we explain it, let us go to this force on a dipole in a non-uniform electric field. Previously, we have seen that in a uniform electric field, the net force is 0. There is only a torque. Hello?
Yes.
But now in non-uniform field, that means E is not same all over. Of course, instead of taking some 3-dimensional E, it is easy to take a 1-dimensional thing, but non-uniform. Non-uniform field will be shown by not parallel lines, but say some lines like this. I don't know whether you understood. This is non-uniform field. This side E is less, this side E is more. If the lines of force are, field lines are crowded, in that region, people say E is more. Now, let me say I have a dipole placed here. It is easy to do in 1-dimension, children. Actually, after that, we can write a 3-dimensional formula also. So this is at X from some origin, and that plus is at X plus delta X. Do you follow? Delta X being length of the dipole now. E here is E, for example, it is E plus delta E. Naturally, at X it is E, at X plus delta X it is E plus delta E. Just mathematics. Along X-axis we took. Along X-axis, so let us think there is a non-uniform field. Do you follow?
Yes, sir.
And non-uniform field is shown by this kind of lines. If the field lines are parallel, E is going to be same everywhere. I will talk more about this once we introduce the idea of field lines, which I have not done yet. But right now, just take it for granted, not a bad idea. Now, what is going to happen? Can you guess? This will experience a force like this. F on minus, I can say. This will experience a force like this. Because E is towards right? This is F on plus. So the net force will be F plus minus F minus. The reason being, this is E plus delta E, I thought, and this is E is more here. How much is that? E plus delta E into Q minus E into Q. Hope people followed it. So EQ plus delta E into Q minus EQ. So F equals Q into delta E. But I know dipole moment P equals Q into delta X here. Delta X is the length between the charges. So what will be Q now? So if I substitute, what would I get? P into delta E by delta X. So when delta X is tending to 0, I can write F on the dipole in the X direction is P d by dx. So this is the formula for the force on a dipole in a non-uniform magnetic field. That means dipole moment into the rate at which the E changes on X is the force on the dipole. Now, we can explain this attraction of the paper pieces with that. See, the teeth are actually what? Teeth or the bristles are shaped like this. Charge density will be high here on the pointed edges, like the lightning conductors have got. high charge density at the spikes. Do you follow? And here it will be somewhat less distributed, the charges. So this forms what you mean by a non-uniform electric field like this. And this field will induce dipoles in the paper. Paper is also a dielectric medium. Okay. Dipoles are induced there. Dipoles are formed in that. Do you follow? So a force develops in the dipole so that it gets attracted. What kind of a, say if it is like this, if the field was like this, plus charges will be formed this side, minus will be formed that side. And that develops a force like this. So that's why the induced dipoles here get attracted by the non-uniform field of the electric charge, which is formed by rubbing the comb against the hair. Okay.
If there was a uniform field, if there was a uniform field, then what would?
Of course, here you must have seen it's not only attraction, but there will be a kind of a twirling also. The paper pieces even turn. Hello.
Yes, sir.
We'll see what happens with the uniform field also, but we require some more information. What happens in a dipole, we have to see. Okay.
Okay.
What you need to understand is there will be a net force because this experience one force, this experience other force because of the E being different.
Yes, sir. If in uniform field, the forces will
be
zero.
same. So the net force will be 0.
Yes, sir.
It is automatic, right?
Yes.
Now tell me, children, here. Anything else? So this one more formula. So we collected so many formulas now. So we need to pause for a while and do many problems in the assignment. Tomorrow, of course, I'll give the summary and show a few problems. After which I'll give you the assignment. Okay, complete it. We'll be closing it after that.
Done.
Okay, then I'll close the session.
Thank you, sir.
Thank you, children.